Okay, chapter 27, we'll be talking about some quantum physics today. So, long chapter, try to speed through it. First, the discovery and the properties of the electron, we're already kind of familiar with that. Blackbody radiation, moving electrons can radiate light. And then we're going to say, hey, well, we've talked about light as having wave-like properties. Now we're going to talk about these things called photons, which are actually particles of light, as well as the photoelectric effect. So energy, mass, and momentum of a photon. Not going to mention the Compton effect, and a little bit about photon interactions with matter. Then we'll kind of continue by talking a little bit more about the wave nature of light, but also the particle nature of light. So having both wave-like and particle-like properties is called wave-particle duality. And it turns out that matter can also have some wave nature associated with that. Not going to mention electron microscopes. Talk about some early models of the atom. Very important here is going to be atomic spectra and the Bohr model, as well as de Broglie's hypothesis applied to atoms. So, essentially, discovery of the electron in the late 19th century, we had these things called discharge tube that emitted these things called cathode rays. You may be familiar with the old CRT televisions or computer monitors, cathode ray tube. Essentially, all it really is a vacuum tube, and inside of it we put some gas. Now, what happens is then we put some high voltage across this guy, so we have a cathode negatively charged, the anode that's positively charged, and we have a whole bunch of electrons that are hanging out at this high voltage source. It's going to essentially ionize the gas, and the electrons are going to shoot through some screens, coming out this end right here, seeing some glow. What we then kind of discovered is if we had this high voltage anode or cathode anode shooting some rays out the side, that we could deflect this, three different paths, A, B, and C, if we had some electric field or if we ran some current right here. And then we were kind of taking a look at these rays, and we put them into a magnetic field and noticed that they circled round. Seems like everything from chapters 16 through 20 are coming back to haunt you. And we could measure kind of the charge to mass of this guy. It's going to be related to the electric field that accelerated them, as well as the magnetic field that's causing them to circle around in some radius of length r. The result of this was the E over m, charge to mass ratio for these rays, or electrons as we now know, which is just going to be 1.7 times 10 to the 11th coulombs per kilogram. It really didn't take physicists very long to discover that these cathode rays are actually called electrons. And now we know their charge to mass ratio. But the thing is at that time we didn't know the mass and we didn't know the charge. So this fellow by the name of Millikan devised an experiment that was intended to measure the charge of an electron. Essentially, what he did was he put some oil in an electric field, and the oil had some charge on it. Kind of a heuristic diagram of what he did was he got some oil and he squirted it between two plates, and there's some electric field between these two plates. And he's watching the droplets fall with the telescope, and essentially when they adjust the voltage until they stop to fall, and here they're going to have their weight, their mass times gravity in the downwards direction, and they're going to have the electric force, which is the charge times the electric field, in that direction, and when they balance themselves out, he could essentially solve for what the charge is, because you know the density of oil, you can solve for the mass times gravity. Now, and what he kind of noticed was this charge always came up in integral multiples of the smallest possible charge he could have, E. So he would see 1e, 2e, 100e, 1000e. He would never see 1 1/3 E, 2 2/3 E, something like that. So this let us pretty much solve for this charge that we came across in some of the earlier chapters. And since we know the charge to mass ratio, we can calculate the mass quite simply. Now let's shift gears just a little bit and talk about radiation. We know that radiation is caused by wiggling electrons, and now we've kind of talked about how we discovered the electrons. Now, this fellow by the name of Planck said, okay, well, wiggling electrons cause radiation, therefore all objects are going to emit radiation because they have wiggling electrons in them. He said that the total intensity is going to be proportional to the temperature of the forth. Temperature is kind of related to how fast electrons are wiggling back and forth. And he called this thermal radiation. He said a black body is something that's going to emit only thermal radiation. So you kind of think about it, pretty much everything has a temperature, so it's going to be emitting thermal radiation. We also can kind of say that the spectrum, or the range of frequencies emitted by a black body, it's actually been measured quite well. And we found that it's actually kind of a peaked curve, as you'll see on the next slide, and the frequency is going to be directly proportional to temperature, at least the peak intensity. And this curve just kind of shows that the frequency is going to be proportional to the temperature. Essentially, if we have something that's 300 degrees Kelvin, it's going to be emitting some radiation. However, it's actually going to be closer to the infrared. We're not going to be able to actually see this peak frequency right here. You heat the object up, 4500 Kelvin, still not quite in the visible spectrum. Maybe it's just barely starting to glow red a little bit. Heat something up some more. Now the electrons are wiggling faster, and now we're going to be able to see this. The peak frequency is going to be directly in the middle of the visible spectrum, and this is actually the temperature of the sun, so it should be kind of a yellow-greenish type of color. Now this spectrum, this blackbody spectrum, could be measured by people in the 1800s. However, they couldn't actually fit curves to it, so they weren't too happy about that. Max Planck in the 1900s proposed a solution. He said that the energy of these atoms that are oscillating can't just have an arbitrary value. It's got to be related to the frequency. So he said that the energy is going to be equal to some constant named after him, the Planck's constant, multiplied by frequency. And Planck found the constant that was named after him essentially by fitting the blackbody curves. 6.6 times 10 to the negative 31st joules multiplied by seconds. Now, this is a new type of physics. This is not classical physics anymore. This is saying that energy has to come in integer multiples of the frequency. So there's going to be quantization of energy. Energy is now must behave in discrete little packets, pretty much the way that charge is quantized. We are not going to have any charge smaller than the charge of an electron. Now, so also must energy. So quantization, this is the kind of the birth of quantum physics. Now, Albert Einstein actually said, hey, this is a great theory, let's take it a little bit further. Light must exist as a set of small energy packets. So here we're going to have energy, and we're relating the energy of the light to Planck's constant multiplied by the frequency of light. So these tiny little packets or particles of light are what we call photons. And we can kind of see that if we had a frequency of 1, so frequency is equal to 1, the smallest bundle of energy that we could possibly have is going to be 6.6 times 10 to the negative 34th joules. That's the smallest unit of energy. This led to the discovery of the photoelectric effect, which is actually what Albert Einstein won the Nobel Prize for, not his theory of relativity. Essentially what we kind of do is we take a light source and we shine light onto something that is sensitive to light, and it's going to start to pick some electrons off. So these electrons are going to come off the metal. We put this thing across a voltage, then these electrons are going to approach our point C. Turns out that if the frequency of the light is too low, then we're not going to see any electrons. And as we went ahead and we increased the frequency of the light, so also did the kinetic energy of the electrons that popped off. So increase the frequency, increase the energy. Decrease the frequency, lower frequencies, lower the energy, or perhaps none at all. So here's kind of the funny part. If we treat light like a wave, then the theory would be, for the photoelectric effect, that the number of electrons and their energy should increase with intensity. I shine more light on there, more electrons should pick off. Increase the intensity, I should also be increasing their energy. Frequency should not matter. However, that's not what we see with the photoelectric effect. The number of electrons depends only on the frequency, and increasing the amplitude is not going to increase the energy of the electrons that are picked off. If now we said that light is particles, or photons, then this theory is going to predict that increasing the intensity is going to increase the number of electrons, but not have any effect on the energy. This is kind of what we see. It also says that there's going to be some minimum energy required to break the atomic bond between the electron and the positively charged nucleus. And the kinetic energy should increase linearly with frequency, pretty much as Einstein predicted. So increase frequency, energy goes up. It also predicts that there's going to be some cutoff frequency, below which no electrons are going to be emitted regardless of the intensity of light. And essentially what Einstein did was he plotted the energy versus the frequency. And so got kinetic energy of the electrons over here, got the frequency over here, and you can kind of see right here that there's some frequency below which there's going to be no electrons emitted, and this is going to be the energy required to break the bond, to pull the electrons away from their positive charge. So what Einstein shows is that this is clearly going to be that we need to treat light as little photons, not as waves. So these particles that are called photons, they have to travel at the speed of light. I mean, it's light. It travels at c, 3 times 10 to the 8 meters per second. Now, we haven't really talked about relativity that much. Actually, we haven't talked about it at all. So you're going to have to kind of trust me on this. We're going to have to use some relativity to write the momentum of a photon to the energy, as well as to Planck's constant and the wavelength. So at the end of the day, we write that the momentum must be equal to Planck's constant divided by the wavelength. Now, at this point, we're in a bit of a pickle here. We have phenomena such as diffraction and interference that clearly show that light is a wave. However, there's things that also blatantly show that light is a particle, such as the photoelectric effect. And the question is, which one is it? Is light a wave or is it a particle? And it turns out that we really don't know. We pretty much have to accept that there's going to be some dual wave-particle nature of light. This acceptance that we have to do is actually called the principle of complementarity. And what that says is there's going to be some wave natures of light. There's going to be some particle natures of light. This is just fundamental to light. And really, if you kind of think about it, whether it's a wave or whether it's particle is really just our interpretation of how it behaves. The truth is we really don't know. The way that I kind of always think about it is if light is being emitted or is being absorbed, then we're going to treat it like a particle. And if it is propagating, so going through slits or something like that, then we're going to treat it like it is behaves like a wave. Now, that's kind of a mind-breaking concept that photons can have both wave-like behaviors as well as particulate-like behavior. Albert Einstein then said, well, if this is true for photons, why can't this be true for any type of matter? And it turns out that he was actually right. We can say that all matter is going to sometimes behave like a particle and sometimes behave like a wave. And it turns out that we can write the wavelength of any matter to be related to Planck's constant, as well as the momentum, which is again just simply going to be the mass times the velocity. However, we're not going to see the wave-like behavior of most ordinary objects. Let's consider a baseball for a second. We say this baseball has a mass of 100 grams and it's thrown at 50 meters per second. So we could say that the wavelength is going to be Planck's constant, 6.6 times 10 to the negative 34th, divided by the momentum, the mass, 0.1, multiplied by the velocity, 50 meters per second, let's just say. We type that into the calculator, we're going to come up with 1.3 times 10 to the negative 34th meters. This is an extremely small wavelength. If you think about it, visible light is in the 400 to 700 nanometer range, and that's times 10 to the negative 9th. This is times 10 to the negative 34th. So we're never really going to see the wave-like behavior of ordinary matter. However, as the momentum, as the mass times the velocity starts to become smaller and smaller and smaller and smaller, then this wavelength becomes larger and larger and larger and larger, and we can see the wave-like behavior of very light particles. For example, the electron. So electrons, we know what their mass is, and kind of a typical velocity of an electron might be 5 times 10 to the 6. And so we can go ahead and calculate the wavelength of an electron, 6.6 times 10 to the negative 34th, that's Planck's constant, divided by the momentum, 9 times 10 to the negative 31st, fix that guy up there, 31st, and then 5 times 10 to the 6, and we're going to get a wavelength that's on the order of 10 to the minus 10th meters, which is roughly 0.1 nanometers. Now we're starting to talk about wavelengths that we can actually be able to detect. What this means is if we pass electrons through a crystal, then it's going to be diffracted. It's going to exhibit some wave-like behavior. So kind of the image that you're looking at right here is going to be electrons that were passed through matter, and you can kind of see that there's going to be some clear diffraction going on here, where we're going to have a right band right here, and then a dark band, a bright band, a dark band, a bright band, a dark band, a bright band, a dark band, and another bright band. So electrons do exhibit some wave-like behavior. Practical application of this is, if we think about optical imaging, it turns out that the smallest object you can resolve is on the order of the wavelength of the light that you're illuminating an object with. This is diffraction limited. However, if you think about the fact that the wavelength of electrons is very, very, very small, that means that electrons can be used for imaging. They can resolve objects quite well, and with a much finer resolution than we can with visible light. This is kind of the principle behind electron microscopes. So now that we have a better idea for what the electron is and how it behaves, let's take a step back and start to take a look at some of the early models of the atom, the building block of matter. We knew by the late 19th century that atoms were electrically neutral, so we knew that there was some positive charges and some negative charges all kind of wrapped up in a bundle. And better yet, we knew that they could become charged. We could separate this charge out, and so there were positive charges and negative charges, protons and electrons, if you will. One of the first models proposed was in 1904 by a British physicist by the name of J.J. Thomson, and he proposed kind of a plum pudding model, and British plum pudding, think of it like raisin bread, if you will. And this atom here had just kind of a bulk positive charge with some negatively charged electrons kind of wrapped up inside of there. And you take a look at it, it's net neutrally charged. It's got positive charges and negative charges. We can separate them out, and it seemed to work. However, around 1911 or so, a fellow by the name of Rutherford did an experiment where he was essentially shooting positively charged helium particles, also known as alpha particles, into a gold foil. So kind of what he had here was he had some positively charged helium particles, putting them through a very, very, very thin sheet of gold foil, and what he observed was not what the plum pudding model would expect, which is, hey, it's going to hit some plum pudding and bounce backwards. He found that the alpha particles actually most of them went through this very, very thin sheet of gold foil. So he's thinking to himself, well, how is this possible? So this is just kind of a picture of Rutherford's setup here, where he had some alpha particles, again, just some positively charged helium particles that he was shooting through some metal foil, and most of them passed through, but they were scattered at some weird, funky angles, and some were scattered in the backwards direction, and some, even fewer still, were scattered directly back towards the detector. Now, if you want to just kind of think about having a positively charged nucleus, again, if this was the plum pudding model, then it would bounce all of the alpha particles directly back at it. However, the only way for what Rutherford observed to happen is he's saying that this has got to be really, really, really small. And so most of the alpha particles are going to pass by. Keep in mind that these have some positive charge to it, and so it's going to be feel a force of attraction, so it's going to bend. And we're going to get positively charged alpha particles just kind of bending around the nucleus, impacting the screen like that, and very, very, very few actually hit this positively charged nucleus head on and was deflected right back to the source. So this really made us think about how made us think about the makeup of the atom. So what Rutherford did is he proposed a different model of the atom, where we have this positively charged nucleus. However, it's really, really, really small, 10 to the negative 15th. And it's got to be net neutral, and so now it's going to have electrons that are kind of revolving around it, with a general kind of spacing of 10th minus 10th, which agrees with the plum pudding model. So most of the atom is actually empty space, so we can have our positively charged alpha particles passing through as such. And again, very, very, very few are going to directly impact the nucleus and get scattered in the backward direction.